Welcome to the session, Sparking Success, Apache Spark on Kubernetes. Thanks everyone for joining today. This will be a 15-minute talk, just a lightning talk, to talk a little bit about some of the things that we as Neo Financial have learned across this journey. Just to get things going, who am I? So I'm Pedro Pichatelli. I'm the data infrastructure team lead here in Neo Financial, company based in Calgary. We're a fintech trying to win the market. I have around 7 years of big data experience, been leading the team, like I said. I specialize on building data platforms across companies. It's basically what I enjoy doing the most. I am Brazilian born. I migrated to Canada around a year ago, and I can't play Counter-Strike in English. That is super sad because I love the game, and after I moved, I just simply can't because there's a lot of muscle memory that involves playing the game. So there's those like spots where you call out where enemies are, and I just know all of them in Portuguese. And in a fraction of a second, my brain can't translate them. So I actually cannot play Counter-Strike in English. But yeah, if there's any Portuguese speakers, then hit me up. We can play some lobbies. Cool. Before we get into the lessons learned, let me share a little bit of context just so you understand where we're coming from and how do we think we now are able to share some insights over our implementation. So across this 1 year running in Spark in Kubernetes, we had more than 500,000 successful Spark applications just in production. I'm not counting staging, integration environments, not counting any load tests or POCs. This is just production as is. We basically spun across this year thousands of daily nodes. Most of our jobs run on ephemeral clusters, meaning that the clusters go up, process what they need, and then they go away. And that requires some different building than having like this forever running cluster there available. We run both stream and batch workloads in this implementation. I would say it's a 50-50. For every stream, there is also a counterpart of batch to make that data look better in the later stages of the pipeline. And we are empowering 9.9 of mission critical reports and data analytics. The reason I say that is because there is one report which doesn't run from the data platform. And for that reason, I cannot say 100, which is unfortunate, but that's fine. I can take 99. So one of the fun facts about our Spark on Kubernetes implementation is that it's basically 50% cheaper than our previous solution. Before we were running a vendor, and the whole implementation is a little bit different, but the idea is the same, right? We just want to have Spark applications here and there. They want them to process something, either if it's streaming or a batch workload, and then go away. So we decided to take this step a year ago and just like, get our vendor out of the way and decided to start hosting our own Spark on Kubernetes solution, which proved to be really cost effective, at least for our use case. So before I say that everything is rainbow and, and colorful things, I just want to have like a quick trade-off disclaimer here, which is about Spark on Kubernetes might not be for you. It's hard to say. I prefer to say this in the beginning rather than the end, when you get all excited about it. The idea is whenever you trade like a software as a service or a platform as a service to an infrastructure as a service, there's always this trade-off between features that are already available, maybe tons of developer time available from that vendor to fix some bugs and things like that, where if you're hosting everything, you have to rely a lot on the community itself, so Spark community, and also your own infrastructure team. So be aware of this trade-off before you make a decision like this. There's more responsibility, so let's say if there is a outage in the solution from your vendor, you just basically can't do a lot. But if there's like any outage in your Spark on Kubernetes implementation, then you have to act on it. There's no one will save you there, which is something to be careful. New tech requires new skills, so be careful if you're a team lead and you want to make this move, talk to your team, make sure that they are on board into learning this new tooling, because one of the things that vendors do well is wrap up complexity, which probably your team will also try to do in-house later or maybe use another like open source tooling, but ideally someone will have to absorb that complexity that once was wrapped from your vendor side. And fourth is hiring and onboarding will be impacted. Whenever you say that you run something on Kubernetes, it might become harder to hire because traditionally Spark workloads are very well designed to run on EC2 boxes or any boxes in general. And when you change that to a container perspective, this might have some impact in terms of skills and hiring as well. Cool. Now, as the fun part starts, I'd just like to share some of the key aspects of this deployment. These are lessons learned we got from this 1 year of deployment. These are all the things that we have changed in the past that actually made our whole solution much, much better than it was before. So just to start, I think the kickoff is using Spark on Kubernetes operator. This is an open source project maintained by Google itself. Basically, this robs a lot of the complexity of submitting Spark jobs to a Kubernetes cluster. And basically, this will allow your team to get going faster. It has some drawbacks that I will explain a little bit more, but it's a great kickoff for your team. If you have no idea, you'll never run anything on Kubernetes when it comes to Spark, this wrapper helps a lot, this operator helps a lot. The downsides is that the Kubernetes autoscaler, the native autoscaler, doesn't work 100% well with this thing. The main reason is the operator has some custom resources which the Kubernetes autoscaler doesn't understand. So it's hard for the autoscaler to spin up and down nodes sometimes. Like it might not recognize that your pod has to keep going and it will try to shut down that node, which makes you lose some Spark applications. Or it will try to keep the nodes alive even though you could collect them because all the applications were done. So another drawback is that the code base improves very slowly. It's been catching up recently. The repo is much more active than it was like for the past 2 years or something. But it's good to notice that for a long, long time, this code base was a little bit inactive, which means that some of these things that I'm talking might have been fixed if there was more activity in the repo. There are tons of open PRs, so the community is trying to give in. But since this is a Google-managed repo, they are the only ones that can actually merge code. And they do this like on a more controlled pace, rather than something like Apache Airflow, which has like tons of PMCs there just for that. Another great win for us was adding the pod disruption budget. This is a mechanism of Kubernetes to allow you to say these pods cannot go away, these pods can go away, and for those that can or cannot go away, keep X alive. So basically what we did is we decided to implement a PDB, which is the short term for pod disruption budget, just for the driver pods. The reason is on Spark workloads, the driver is the most important piece of the whole execution. It cannot go away. If the driver go away, the Spark application fails instantly. But if the executors go away, then the driver can request for newer executors and it can go on. So if there is like a very unbalanced node that the autoscaler is trying to recover, then it's just okay to lose that executor, pass it to the next executor that is getting spun on a new node that has more of a balanced workload. Not everything needs PDB. That's also great to say. Like that you might have integration workloads, staging workloads, so non-production things which don't really require a PDB. And you also might have things that can fail. You know, they're not mission critical, so you can allow them to fail because of this auto-scaling mechanism. The PDB will prevent just the autoscaler from collecting your things. Another quick win that helped a lot is using t-shirt size clusters. The idea here is basically if you just expose a bunch of numbers to your users, they will get confused. Not every Spark user wants to know the whole aspect of Spark. And if we go back to the vendor idea, they rob this a lot as well. They basically offer you limited amount of possibilities. They try to limit some combinations there. Whenever they provide you a combination, they try to optimize for that. So it's a good idea for you and your team to try to do the same. And t-shirt size clusters work well because normally workloads can be defined without looking at the actual code into like small, medium, large, and X large, and things like that. And it also can use different sizes for different environments because probably if you're not running in production, you don't need the same size as you run in production. And then this also helps your team to be able to optimize those sizes and leave just one custom for scenarios where it won't be possible to actually use any of those. Something else that it's awesome for us is the node pools. Node pools is basically an idea of Kubernetes of adding multiple instance types and sizes into something they call a node pool, and then you can attach Spark jobs to this node pool. The idea is, in Neo, we set up a couple of different instance profiles, meaning that if you're running on a spot instance, it means that you can have some flexibility there in case one of the families is pretty busy in terms of availability. Another thing is you can also mix on demand and spot, which is great because if you're like, we're having Black Friday, and during Black Friday it's very common that spot instances are not available. So you want to have that fallback mechanism of going to on-demand, which is much more expensive, but that's fine for like an outlier such as Black Friday period or holidays period or something like that. So exploring those flexibilities could help you a lot. And also, whenever you're choosing different sizes or different family instance types, make sure that you keep the same memory and CPU ratio. The reason I say that is because you will want to tune the Spark configuration for those ratios. So what I mean is, if you're running one core for 8 gigs of RAM, keep that on any family type or any size that you're running. Don't run something like a 1 to 8 and then a 1 to 4, because when that 1 to 4 instance is chosen, it might break the whole Spark application because of the Spark tuning that you did. So tuning dynamic allocation is also very important. Dynamic allocation is Spark mechanism to upscale and downscale. And the thing is, the vanilla values are pretty greedy. Probably some vendors already tuned that as well, and for you, it will be just the vanilla values available at the beginning. So make sure you play around with those two. There are basically 2 parameters that define the majority of how the dynamic allocation will work. So you can play around with those 2 values and understand like how is it going, if it's faster, if it's too greedy for what you're trying to do. Sometimes we want the autoscaler to be more let's say, to be faster or more sensitive, because that workload is very critical. And sometimes we can just leave it running struggling for a little bit until we actually spin new instances, just because it's not mission critical for the company. And make sure that you have some preset values that match those t-shirt size clusters that I spoke before. This will help you a lot. Another thing that might help you folks is the node decommission feature. This is a feature that is way more important in Kubernetes than the classic boxes and yarn implementation. The main reason is when we are running on boxes, whenever a Spark application fails, it's kind of like a process failing in that instance, which means that we can kind of use some sub-processes still before the instance gets recollected from whatever is managing the resources. In Kubernetes, when a pod fails, it doesn't matter the reason, Kubernetes will take it away. So the node decommission helps in terms of Spark, whenever it fails, or whenever there's a downscale request from the cluster, it will basically find another executor and will copy all the data, the shuffle data from the last stage into that executor in order to keep the job going without any problem. So this makes it, not that the application would fail, but whenever a stage fails, the stage has to be recalculated by whatever executors you have available, meaning that there's overhead added there. Also good to notice that this should become available possibly in the future. The main issue is this difference of nature from the boxes and containers makes it very hard to implement an actual external shuffle service and other things in this domain. History Server is also a very good ally. History Server will help you to enable after-the-fact analysis. So basically, whenever something fails 3 a.m. and it's not mission critical, you don't need to wake up an engineer. You just basically keep going, keep sleeping like always, and then come to the office next day and then get the logs from the history server and then see what happened there. See how was the memory pressure, CPU pressure, network, disk spew, things like that. And enabling that will help you tremendously with debugging and also tuning, because that will give you, let's say that you're trying to tune a specific workload that's running every hour, and you can leave it running for like 3 days and just collect the metrics after and do some sort of analysis of like what parameters work best for that workload. Also good to notice that this requires a bucket to land the data on. So make sure that you put some sort of time to live in the objects there, because otherwise the build might get pretty expensive. So probably you can keep around 30 days of history there, not more than that. That would be an overkill. Cool. So I always like to end my talks with some inspiring quotes. This is a quote from our CEO, Chris Reed. He always says, "We are hiring," and we actually are. So feel free to hit me up or to go to our careers page and make sure that if you think that one of the available spots there suits you, please enroll yourself, and I hope we are colleagues in the future. This is Daniel, by the way. He is the infrastructure lead here in NEO, and he has helped a lot in this process, in this project as well. So just wanted to give him a shout out. And the fun is he's 100% human. So not AI, no robot. Thank you, folks. Thanks for having me.
Didn't catch that. All right, thank you so much. Testing, everyone can hear me? I guess, cool. So, does this thing work? Can you try it? All right. So, sorry I didn't catch your cue, Pedro. It's my first time at the DevFest this big. I don't know how it works. There we go. So, thank you everyone for staying until now. It's going to be a mix between technical and non-technical. The goal is more to give you an idea of what's happening in this field called XAI in a way that's technical enough for you to kind of understand the problems, but also in a non-technical way so that you understand the business problems related to it, because it's more of a business and politics problem than it is tech. So, let's start with the beginning. I'm Elyes. I have been in GDE since 2020, as you can see from the number of shirts I've got there with Google. And it's been a blast. I'm also a machine learning consultant on the side. I specialize in education, training, content creation, worked a bit with NVIDIA, as you can see also from the other side. No, can't see this, not used to this. There we go. And while working with a lot of startups, because I specialize in startup mentoring, I found one recurring problem, which is once they have the model built out and put to production because of demos, they have issues usually with the actual predictions. And so that actually got me interested in seeing what could be done. And most of you must know this called robustness and out of distribution generalization. But the better term for it would be explainable AI. And so I want to go in that, and that's why I am currently pursuing a PhD. So I put my job on the side, and I'm currently pursuing a PhD in explainable AI and cybersecurity specifically. And I just became a candidate 2 weeks ago by the very same slides I'm going to present to you. So let's get right into it. There's a lot to cover. We are going to talk about mainly opportunities, but mainly the challenges, because we want to implement a real-life explainable AI pipeline that can be used in any problem, right? Well, the pain points is, as much as you all might know, AI is in every single app. If some new app comes there that claims to have AI, you're good to go, you're adopting. And it has been proven to be as performant so much that we now use it in critical applications and critical domains such as autonomous vehicles and cybersecurity. So far, so good. The issue lies with these small times where we get some headlines that look like the Amazon discrimination problem, the Google photo racism problem, and the autonomous vehicle crash problems. And when you're not technical, you would see this and say, what happened? So you're like afraid of the technology. You say, OK, don't trust robots. There's a problem going on. But if you're more technical, you would ask, why did that happen, and how can you prevent that? And that would be the goal of explainable AI. So let me get into it. One of the issues of machine learning is the metrics that you currently use. So you might know some of these, like accuracy, precision, and recall. And the issue is that these are single digits that we use to evaluate the performance. And the issue with that is a simplification of the real problem. So the real world has lots more of details and ramifications, but we are trying to compose them in one single digit. And there's only evaluation. What happens is, if you've got a model, like this one, that classifies it, it's going to do well. So the loss is going to towards zero. It's going to converge. But the issue with this kind of problem is that while it's performant, it's a math equation. So there's lots of ways to solve a problem. Meaning that when we have a data point that we want to predict, classify, the model could give us this kind of result. So it's a class 1 with this probability. That's not what I want. This is my question. My question would be, why is this that class? Why that probability? Why not? When do you go wrong? How can I protect myself from that? And that's the issue with the current things. What we ideally want would be a justification, a because. And with that, we'll be able to completely master the model that we have and the issue that we're working with so that we don't get sued afterwards, we don't get blamed for any problems, etc. So the science that does this is what you call explainable AI. And in a nutshell, it's just a way to go into a model. It could be a black box. It could be an interpretable model. It could be an API. So even if it's a simple nearest neighbor model, if it's behind an API, I don't know what it is. It could be anything. So it's a black box model. And the idea is to go into that and try to export some explanations to the users. Could be in the form of feature importance. In financial problems, it could be hey, these are the most important features for deciding to give you a loan or not. In an image classification or segmentation problem, it could be like this. So you'd use XY, for instance, to generate a map that tells you these are the pixels that most classify or most support our decision. Or you could go into something more, let's say, stats-based and generate some rules and say, all right, this group with some values can be directly classified with this precision and this coverage of the data. So this also could be kind of an explanation. Now the issue is these are three examples from 3 algorithms, but there's tens more. And you might ask, what do we need? Which one would be the best? Well, it depends on who asks. So for all the domains and industries that there are, some of them are obligated by the law to add explainable AI into their systems. They can't not have it. Others are forced because the errors could be fatal, so human loss, money loss, etc. And some are just forced because, well, they have to keep up with competition. Otherwise, they just lose their client base. Now, you might say, OK, so all of these need explainable AI, right? So you'd say, OK, that's cool, but why doesn't everyone have one in real life? Why don't you really have it? Well, it's complicated. Let me give you an example. The XAI pipeline would look like this. You would have a model based on that does some task, based on a data set, and you have a question. Depending on these factors, you would choose the explainer. So the explainable AI algorithm that generates the explanations is called an explainer. This explainer generates an explanation to a certain audience. That explanation has to have some desired properties or desired traits called desiderata. Now, again, depending on this, it could change. So let me give you an example. If we had a neural network that classifies images, and the question is, why did it misclassify an example like 1? We could use GradCam to generate a saliency map that could be comprehensive or concise, depending on if the audience are developers or users. And the saliency map would look like this. So that's a dog, that's our neural network, it classifies that, it says, hey, it's a dog, I want to know why. So in a comprehensive way, it gives me all the pixels that have a feature importance. A concise way would maybe focus on just the face or maybe the paws or something like this. But this is one type of explanation. And it could really help when, for example, instead of having it this way, you would have something here, and there should be nothing there. And it happens when sometimes you've got a background problem. So wolves would be in the snow, while dogs would be in the park. Green background, white background. So that would explain there's a problem with the data distribution. So anyways, this is one example. You could have, for each one of those blocks, hundreds of different values, right? So the question is, what do we do? How do we choose? And that's the question I'm trying to answer in my PhD. So spoiler alert, there's no answer to this. I'm going to share with you what I found and what the pain points everyone is, and it's up to you then to glamorize, find some solution to it. All right. The good thing is that researchers did come up with definitions, tools, algorithms, and depending on your need, if you're just trying things out, you are just experimenting, just choose one of the tools and algorithms. But if you are in a DEFCON 1 situation where you're getting sued, you are getting hammered, you're going to have to close your company because of a misclassification, then you have to go more technical, and that's what we're going to do together. So let's do a small literature review, but like executive summary of what's currently happening. First things first, you got a model, nice. Now, we want to explain the model. We want to know what's the bias, the weaknesses, what could happen, like what could wrongly happen, right? So the first thing would be to choose the right algorithm or the explainer. And there are lots. I'm going to spare you the details. There are hundreds of them. These are some of the most used ones. I don't know if they're going to share the presentations with you, but all these numbers are links to the actual papers. Yeah, I'm a scholar, sadly. The ways that you could classify, yes? Oh, I thought this was a question. So the way that you could classify these algorithms would be based on these characteristics. So leverage is the type of technique that you use to generate. It could be proxy model, so you take another small model and you try to train it to have the same distribution. It could be feature attribution, where you change the values of a single data point and see how it changes the confidence scores, or something else. Compatibility means with what type of explainer could we use this. So agnostic works with any model you have, anyone. But neural network, but some of them only work with some specific models, like IG and PIECE in this case, because they use gradients to calculate the difference. Granularity basically locally means one single explanation, one single instance that you want to explain if someone has a problem with explanation. Global means all of the data, so you want to know more of what are the biases learned by the model. Explanation phase, I'm going to leave it for last. And format is, do you want images, vectors, or text? As easy as that. So for instance, if I work cybersecurity, we have APIs, we have text. We don't really care for images. For image classification, you need images. OK, explanation phase. All of them are post hoc, which means, are we generating the explanations at the time of training or after the training? And all of them are post hoc because simply the models that can generate explanation at the time are interpretable. We don't need explainers for them. So if you have a decision tree that's interpretable, you don't need this. You could, but you don't need. And to know the difference, we've got if the model in itself could be used as an explainer. Sorry, if the model needs an explainer as a post hoc, then it's a black box model. So we have no access or understanding. It could be a neural network. We have access, but we don't understand how it works. Could be an API. It's an easy model, but you don't know it's an easy model. Then you've got the interpretable model, or white box, which means the model is inside the explainer. You could just do model type model dot feature importances, and you got the answer. So we have an access or understanding, so KNN, etc. In the middle would be the gray box models. I'm just going to skip this, but imagine this is like ensembling methods, decision tree, random forests. You've got lots of them. You know how each works, but the combination is kind of fuzzy sometimes. So what we want, so what currently is we've got a performance scale and interpretability scale. So the easiest models are the most interpretable, and the most performant are the least interpretable. What we want, ideally, is to step-by-step go into this space. So high interpretability with high performance. And what we could also do is start from these ones and try to make them more interpretable. There are two ways actually to work on this. The explainer methods, the explainable AI method would do this. They take a performant model and try to make it more explainable. While in real life, lots of startups just use these. All right. Now, we might have a list of algorithms. So you would say, how do I choose? I got 2, 3 ones. They're nice. Well, there are metrics. I didn't know they used them. One of the metrics is explanatory power. So the explanations that are generated, you could use them. You could test them on actual tasks, semantic tasks afterwards. So let's say use an LLM to explain a model. And you got 2 candidates. And then you just use those 2 candidates as input to another model as a semantic task, like toxic command classification, for instance, or let's see something else, I don't know. And the one that scores higher is better because it's got more relevant information. So that's one way to do it. We could also see, so transparency would see, causability would see if the explanation has cause and effect. So it would show you step by step how we went there. And there's lots of others. I'm not going to go into details, but now you know there are metrics. One of the issues is that these metrics aren't easy to code, let's say, because there are tools that allow you to do this easily. So these are some tools. A lot of them have multiple algorithms. A lot of them are general purpose. And a lot of them are coded in Python. So that's nice. But one of them incorporates metrics. So it would be the first one. And you could use those as a way to know which is the best explainer. But the biggest issue would be no selection guidance, meaning that you would have no idea which one to start with. I could go with anyone. The issue is that SHAP takes 15 minutes to generate something. Lime could take 3 minutes. But PIECE and Anchor could take an hour. So I'm not going to try everything out. So this is one of the issues that you currently have, selection guidance. I looked into the taxonomies, and taxonomies just is a fancy way of saying ways to classify things. And the most recent would be these 4 works that covered algorithms, and some of them have selection guidance. So let me give you an example of what it looks. A normal taxonomy would look like this. I love this. All of the explainable AI algorithms are the most popular ones. I don't know if you can see them, not really, but all of the most popular ones got classified by family type and characteristics. That's nice, but doesn't help us choose the first one. The second one, however, is better. It's a baseline, but at least you have a start here. Transparent model or rough explanations. Depending on your answer, you go to either one of these, and then you have another type of question. So it kind of guides you, and this is what you want to go into. It's a good basis. There's still improvements to do. Specifically, like this works on R packages, but this is a good, let's say, improvement area when I go in. All right. So last thing in the algorithms would be the strategy. So I laid out how there's a lot of factors, let's say, or variables, but some strategies that we currently use. One would say choose the algorithm that ticks the most checkboxes, that does the most things, all the granularity, all the compatibility, all the underlying techniques. That's nice, but that's not what we want. That's versatility. It does everything. It doesn't mean it's good for what we want. There's a difference. It's not effective, let's say. Another one would say use the most popular cited ones. Yes, but that introduces publication bias. We just keep reusing the same most known ones, not technically the most efficient ones. Use one that was used on a similar problem. This is a good approach if you have the time, because you have to get the same distribution, the same data shift, the same features, all the same details of the problem. Otherwise, it's not going to work. Then you could say, all right, let's group them by criteria. Try one of each family. This is also nice if you've got, again, the time and the budget, because one piece explanation, was it piece? Piece takes an hour to generate. I'm not going to play with this a lot. I don't have the time and budget for this. This is the most used one. Use the one you master. That's not bad. The only issue would be that sometimes it's inefficient, incompatible. If you are proficient with Lime, well, I'm sorry, but Lime can do global explanations. Sharp can do that. That would be the most general one. But even Sharp sometimes has a problem with text. So I worked on a text cybersecurity problem. And Sharp is not made for text. It's made for features, like tables. And so we had issues with frequency of words. Some words appeared one time. They had much higher score than others. We had to take the Sharp scores and try to normalize them. And we don't even know if it was the best thing that should have been done. Finally, no clue, don't know. Just try multiple ones is the most accepted scientific approach to this. And even with this, code compatibility, one would use a library from 2019, one would be based on PyTorch, one would be based on TensorFlow. There's a lack of framework. That's the issue that you currently have. That's the problem. All right. So suppose that we did manage to overcome this, we managed to choose the right algorithm, we are now trying to make the explanations, right? Well, one model, one explainer could generate multiple explanations and types. So now we have another problem choosing the right explanation. And this depends on several factors. So here are some examples. You already seen some of them. This one from Sharp, from Anchors, again from Sharp, another plot. This is Lime, and it just gives you all of this at the same time. You can't differentiate. Which one would be the best one? Well, it depends on 4 things. First, the goal and the audience. So if you are still training the model, the audience would be the technical team. The technical team is interested in improving the model to be able to improve it, right? So they need something that's useful and can be acted upon for the next sprint. If it's already production, so it's it's the inference phase, now we are dealing with the end users. And these people need to understand the decision itself, because the decision could be on their own, like loans, medical application, something that concerns them. So they want to contest the decision. And these need to be easy to read and to understand. Otherwise, they're going to just call the hotline, and that's not what we want. Then it would be the audience again, so we can go more in specific, because front-end users just want to get convinced, and you want to build trust with them. Developers need to learn the model behavior. Managers just want to better communicate with other directors, the public, and the developers. And finally, executives need to conform to regulations and laws. So again, if GDPR applies to you or DARPA applies to you, what type of explanation would be conformative to the laws? It's bigger than you actually it's actually bigger than you think when you start working on it. Then we need to define the explanation. So once you know the goal and audience, this is the most boring one, I'd say, and the most difficult, because there is no consensus on what's considered an explanation, which is good news, because you could do whatever you want, which is bad news, because you could do whatever you want. So there's no way to, let's say, organize this? I don't know. I got the French word. So these are some definitions given by some individual authors. You would see they allow users to reach their goals. It's an answer to a why question. It's good when you can keep asking why. These are not bad, but they're not structured. You can't really say, all right, this explanation is an answer to a why question. Anyone could do that. So it's not what you want. What you want is something more structured. Well, one survey identified over 40 definitions. And my favorite would be the non-gov, the second one. Details how a AI system's output is determined. So we know exactly what happened to get that. And from there, you could take that explanation and analyze it again and generate what you want to do from it. So my favorite would be the second one for now, but each source has their own definition. So we need to take a look at that depending on our client and the audience and the partners. Right. Types and traits should be the last two things. The type would be what type, like the explanation style we aim to provide. So you got some choices. What gets returned? So is the explanation a data instance? So for instance, they might ask, all right, give me an example where your rule does not apply. Yeah, give me an outlier. And you would give them a data instance that does not apply to the rules that you learned. So they would say, yeah, no way this distribution of people would do that. I beg to differ. Here are 3 cases. Same thing for an autonomous vehicle. No way it would ignore a stop sign. Here are 3 instances where it happened. Rules would be the patterns that learned, feature importance, you've seen that, and the summaries. You could also choose a format. Do you want images if it's easier to see for an audience, for instance? Text if I want to really read into the details. Tables, functions, numbers, graphs, vectors, depending on what you want. And finally, the tone. Do I want to justify? So give why not? Do I want to inform? Do I want to show the mechanism behind it? It all has to be taken into consideration. Finally, the traits, these are optional, so that's at least one thing that you don't need to care about. But optional would be how you could make it better, so from good to great, right? Selected this is my favorite again. So being non-general based on only a few main factors, because if I have a malware classification, like an antivirus and have 250 features, I'm not gonna read all of them. I just want the 20% that give the 80% of decision, and the rest, I could just manually go through that. Yeah, so these are the traits. Now, again, all this is nice, but even if you go through all of that, you might find yourself with 2, 3, 4 explanations, even with that. So we need metrics. And again, there have been lots of metrics. Intrinsic metrics would be the one that assess the quality of the explanation itself without the users. So for instance, clarity would be how easily a human can understand it, so avoiding jargon, use of plain language. Completeness would mean if all necessary information are there. And conciseness would be, is it as concise so that I can really read it and go on my day, right? And others would be extrinsic, which impacts the explanation on the end users. So user trust would say whether the explanation increases the trust of the user in my AI systems. And this is really important. So autonomous vehicles are one of those that need this because we are scared to get into something that could kill us. Same thing for medical device, military device, anything that could create some kind of fear, we kind of need this. And then user understanding, for example, if you can make better informed decisions, so ChatGPT would get into this. Is it giving us really good information, or is it hallucinating and giving us false information, and you have a false sense of trust, let's say. So these two would be really good metrics depending on the use case that you have. And to make it easier for you to just check it out, I took kind of some hours to make this thing that my professor didn't even look at. All the metrics, and whether they can be directly applied into the format, or you need to go and do some more work. So green means, yeah, you can take clarity, take text, and choose one of the metrics that already exist to say if it's clear, like it's clair in French. I don't know, clarity or not. Same for instance and rules, you can easily apply that. But for vectors and images specifically are one of the toughest to be able to apply because you've got pixels, you have to understand the meaning of the pixels, the groups together of pixels, so it's kind of more of the more difficult side. And then we've got evaluation, so some of them can be automated, mostly the intrinsic ones can be automated, that's what you actually want. And the relevance and sparsity you might see can be applied to anything. And that's because they're actually not metrics, they're meta-metrics, but I just couldn't. Let's just say that it's for your own good. I didn't put them on the site. Meta-metrics do not evaluate the explanation nor the impact of the end user. Meta-metrics actually evaluate around the explanation, some meta features around it. For instance, if you take sparsity, if you've got a heat map, like a saliency map I showed you, sparsity would simply be the file size of the heat map. The less file size, the more concise it is, and this is if you already have a really, really good model. So you have to start with a good model first, and then if the explainer could make a smaller file size of a saliency map, it means it's more concise, so it should be a better explanation than another one with too much noise. Relevance, same thing. So relevance, you take text, you remove some words from the text, you put it in another model for classification, and you check which words and features, when removed, had the most impact on decision score. So these could be used on anything. Images would be just the pixels, remove and calculate the pixels. Text would be the words. Vectors would be the items in the vectors. Instances would be the number of instances, and rules would be the number of rules, as simple as that. So I love these people. One thing to take into consideration, though, is that they're not independent. Metrics are not independent. So if you were to calculate completeness and conciseness, it's really difficult to get 100% on both, because the more complete it is, the longer it is, the less concise it is. You could, if you introduce a third metric, complexity, so less words, but each word would become more difficult to understand, so it's more complex. This works if your audience are tech people, like cyber analysts or developers, so they know what that word means. If not, you can't, because it's more complex, so your audience needs to know more what that word means. Otherwise, there could be a misinterpretation, and that could cause more problems. All right, let's talk about humans, the problem with all of our tech. Even if your explanation is good, the audience could still not understand it. And this applies to anything, presentations, professors, a YouTube video. So the issue with this is that you could have the same explanations, give it to two different people. One would be able to understand and generate some suggestions and improvements. The other would not know what to do with it. So this is one of the issues. So you could make a pipeline. You start with some intrinsic like metrics, like structure, readability, give it to some user, and they don't understand it, while another user could get a worse explanation and still know what to do with it. So it's one of the issues that you currently have with automating the pipeline. Again, we want to make a real-world pipeline. So if you have hundreds of users, you're not going to manually check each explanation. So this is one of the issues we have with automating them, and that's why up to now, human evaluation is still the gold standard of evaluation. All right, last slide before we summarize what we saw is some researchers want to see, okay, what metrics should we focus on if we want to make the good explanations? And they say, all right, we want simple things, general things, coherent things. Yeah, but the issue is that if it's simple, it's not complete. If it's general, it's not specific. And if it's coherent, which means with prior knowledge, it's biased. So confirmation bias is when you only take what you believe in. And that's the issue of all the online debates on Reddit and Facebook and social media. So with this, it means that if you give me an explanation that's against what I believe in, I'm not going to accept it. And that's sad, but that's the reality of humans. And so they tend towards simpler descriptions, which could lead to oversimplification. They say, yeah, right, these two features are why this happened. It's simple, it's general, it's coherent, but it's not enough. So it's oversimplified. There's a lot more to take into account. And this means that oversimplification could lead to bias, skewedness, tells an incomplete story, and this is actually how social media and the media in general is portraying the newest news, trying to get to our emotions, telling an incomplete story. So you have a headline that's it's weird. It's you read the headline and say no way, and then you read the actual description, the actual article, and say, oh wait, this is not really as wow as we thought it was. And that's how we do. And you don't want an explanation, because those explanations could lead you to a lawsuit, and they would take that explanation and give it in court, and you don't want that. So the challenge lies in finding a balance between all of this. All right, let's summarize all of this. Let's summarize this in a simple way. We have two major problems, six actually, but in two major categories. Explanation generation and explanation interpretation. One would be the lack of framework. Everybody tries their best. We meet at events, we talk, we try to learn, and that's how it just goes. Second, too many algorithms, explainers specifically. And third, too many variables taken into consideration, which shows by the amount of slides I had. And then you've got the issue that explanations are descriptive, which means that you read them, but you have to interpret them. So as I said, some people do, and some people don't understand. And this means that the interpretation and the evaluation are up to the viewer. Now let me explain why these are problems. First statement means that there's no clear directives on what to do. Second and third mean that there's information overload. Together, we get paralysis of choice. Paralysis of choice, weird word. 4 would mean there's more manual work to do. 5 and 6 mean, depending on the person reading this, the results vary on the subjectivity, creativity, and luck. And these mean there's fear of misinterpretation, overwork, and micromanagement. So with that, when we start with a model and we want to go to the action plan, it's not as easy as just using an explainer and generating an explanation. There's a lot of obstacles to overcome in the middle. And as you've seen, there's a lot of information to take in, to try, to be able to do this. So it's not as easy. And the biggest issue is all of this takes time and money and budget and humans, like let's say talent, to work on. But the return on investment isn't that great. And that's one of the also reasons why Explainable AI isn't blooming as it should, because you can't make a model out of it, an app out of it. It's more like a break. So before we go to production, we need to do this. And they don't want that. Investors don't want that. They just want the fastest possible, go to market, get some money back, and work on that. So if I have this and I tell them, hey, no, we have some problems, that means we have to delay. That means no money for now. Let's just say they don't like that. So one of the reasons why it's not as popular is because it doesn't generate money for now, until we find a way to explain it better. All right, so do I have any good conclusion? No. Do I have any good advice? Also no. Is there any hope? Well, I forgot, yeah, it's complicated. Depending on the side that you're leaning on, if, for instance, you want to go in academia, there are lots of opportunities. So research in general could be like academic research, could be industrial research. So these would be the keywords that you might need to use. Not only Explainable AI, these are all keywords used in the papers right now that work on this stuff. If you are more interested in industry, well, it gets more complicated, because unless you want to work with a company that already knows the importance of Explainable AI, you have to convince them that they need you. Again, because it's not as easy to calculate return on investment. You have to find a way to tell them, hey, if I do this for the company, this is what you would gain from it. And it's not as easy as it seems, because most of them just say, yeah, so what? That's it. So what I like to use is go to some critical companies and say, hey, do you want a lawsuit? And they would say no. I'd say, yeah, you're going to get a lawsuit. And they say, why? And I would have played a bit and say, okay, do you have a protection against this thing? This thing? What if I do this? And usually they say, yeah, don't worry about it. In the back end, you got it covered, but they don't. So I try to cater to their emotions, to their heart, to their money, their wallet, and find ways to get them to see the importance of it, or say, hey, your competitor did this, or maybe you could find some other ways to convince them. I leave that up to you. Finally, if you got any ideas, personal ideas that you would love to try out and discuss, I am giving this same talk to all the DEVFests actually these 2 weeks. I'm touring 5, 6, 7 DEVFests, giving the same talk, and then collecting everyone on my LinkedIn And from there, discussions are happening, actually. I'm really surprised they do. And from there on, there could be something interesting for you in the future. So I'm going around telling people about this, and maybe there could be some opportunities to work on this. I'm not gonna name any organization, but there could be something that could be interesting for this, research, academia, or other. Anyway, so that's it for my talk. Again, that's my LinkedIn if you want to have a question, have an opportunity, feedback, want to insult me. I'm all open for everything, no worries. And if you got any questions, I'm here. That's it. Thank you. Yeah. So again, I'm cool with any question, actually. So the first one usually is the hardest. Do we have any? Cool. When we don't have one, it means either I do a really good job explaining or nobody understood anything. Oh, we've got a couple of questions. Yes, please.
Are these slides available?
I don't know. Are they? Are the slides available?
Yeah, so actually we're replaying this on YouTube, so I can come up with you there and I'll get something after the conference. Yeah, we'll push them up.
Yeah, because there's like links on the slides they can click on, so it's going to be on the YouTube video. Perfect. That's it. We got another question, I think, here? Yes.
So you kind of had that scale where you have certain models that have a lot of information as to how you got the explanation to the result, and then others that are more performant, like neural networks, where it's more of a black box. Have you looked into further why, for example, decision trees, you've probably worked with scikit-learn, where, no? Oh, okay, like when you do a decision tree in scikit-learn, you can actually print out the entire tree and see each step in the process, what question it asked, and why it decided to traverse either left or right down the tree.
Oh, yeah,
and so
yeah.
that's why it has high explainability, because you can literally see each step that the decision tree took all the way down. I guess my question was going to be, did you look into why some of these models in abstract, what principles or properties they have that give that higher explainability versus the models that don't, like neural networks, for example?
All right. So the question would be, if I would summarize it, what's the property that makes a model white box and what makes another one a black box, right? So what differentiate them?
Yeah, and what kind of abstract properties have you looked into it? Maybe similarities that some of them have between each other?
So there are two keywords in this case. So interpretability and explainability, and they're not the same. Interpretability would just see, it's like transparency. Do I have access to all the parameters, all the values, the coefficients, etc.? And explainability would mean, if I have that, how easy is it to understand, right? So decision trees, random forests and stuff, they are 100% interpretable. You see everything. But the issue with that is it overwhelms you with all of those splits, right? And then neural networks, all right, you got access to the coefficients, but they mash the features together. So I think one of the first things is the fact that you could separate the individual impacts of each single feature, or like say input, and that's actually what some algorithms like XRI and integrated gradients do. They take an input, they try to change pixel by pixel, and then calculate the impact it has on the layers.
Okay.
And so with that, we try to separate each individual feature as let's say impact or decision power.
Yeah, okay, or maybe information gain?
That's
Could you
specific
plug
to
like
decision
Shannon's
trees. So
entropy into that or something? Yeah.
yeah, it could. But the thing is, decision gain, information gain would be specific to like naive Bayes or like decision trees. Nearest neighbors would have like a other issue with like local proximity. It depends also on the problem that you work on. So for instance, if you work in a general, so decision trees and information gain, they split everything, right? So you have a global understanding of what's happening, and they just put in the new instance. That's a global thing, right? But you could need, for instance, nearest neighbors models on a more local context if you have a autonomous vehicle and you've got the learned patterns of the big model, and then you have like the small window of time that you are using the vehicle is working, and you need to actually do both. So you would have the big model and you have the smaller nearest neighbors model, and they would collaborate on trying to understand what should be done given the current circumstances. And so in that case, it would actually be beneficial to start with the black box model and try to see the nearest perturbations that could be done on it.
Okay. And would that be kind of like a form of an ensemble model, or how?
It
How do you
could
make
be.
those work together, I guess?
Yeah, it could be. I looked into ensemble explainable AI. There are some papers out there, but I'm drowning in my explainable AI in cybersecurity context, so I didn't really read that yet. But ensembling explainable AI is something. For instance, Lime does it. Lime, I don't know if you remember, there were 3 different plots out there, and it's up to you to cross-reference. And there is an idea going on that you could apply Lime, SHAP, anchors, whatever, get all of those informations together, and then analyze that information and try to see patterns that are recurrent, see where it's best or not. So this is also improvement. This, at least as far as I know, haven't seen a recent work on the ensembling XAI methodology. So this could be something to work on.
Cool.
Thank you.
Thank you.
Any other question? I'm going to look you in the eye, everyone. All right. I think we're good. Thank you so much for attending and for staying. Hope to see you afterwards in the, there's a after thing, right? After party? Yeah, hope to see you in the after party.
Happy hour.
Happy hour. All right. See ya. All right, Greg, I give it back to you if you want to.
I'll grab your mic. Honestly, thanks, Elyes. Thanks for being here. What a great talk. Again, just another example of the incredible talent and expertise we have. So yeah, we want to invite you all to leave, but go over to happy hour. So that's getting going right about now. And we're going to close this stage down for the evening. But everyone, just thank you so much for being here and being part of this. It really takes a lot. Before you go, if you're not coming back tomorrow, I'm sorry about that. And that's okay. It's a 2-day conference, but we'd love to see you tomorrow as well. Tomorrow afternoon, we're going to give away all the rest of the prizes that we haven't given away. So make sure to come for that. And we have a keynote tomorrow morning as well. So I think that gets going about 10 a.m. So yeah, thanks everybody. Oh yeah, and also you guys, for some of you are here for Pedro's talk from Neo, and Neo is sponsoring the happy hour. So everyone buy Pedro a drink, even though he bought all the drinks for everybody. Yeah.